bit error rate measurements in a noisy baseband line-encoded channel. Following this block diagram, we will firstly model a line-coded transmitter consisting of a pseudo-random sequence generator as the data source, which is then line-encoded. Next, we will model a band-limited baseband channel with added noise. The receiver front end uses a detector block to regenerate the distorted received signal, and then a bit error rate instrumentation section using an exclusive OR function to compare the received signal with a known local copy of the transmitted sequence. We commence by patching together the transmitter section. TIMS allows us to model any transmitter, channel or receiver, either individually or as complete systems. Line-coded data options are NRZL, NRZM, unipolar RZ, bipolar RZ, RZAMI, biphase Manchester, dicode, and duo binary. We start building the channel with an adder block, noise module to add noise in the channel, patching the transmitted signal into the channel and then adjusting the signal gains to the desired signal-noise ratio. Band limit the channel with a filter block of various switchable phase and frequency responses. And you can vary the level of band limited noise. Moving from the time domain, we now trigger on the bit clock to view the received data signal as an I pattern. We can observe and measure signal-to-noise effects on the eye aperture at any levels we wish to set, as well as channel filter phase responses and intersymbol interference effects. With the transmitter and baseband channel modelled, we are now ready to insert the detector. The decision maker regenerates a TTL data signal from the distorted received signal. Like all TIMS modules, it is hot swappable and fully overload protected. The sampling instant or decision point is adjustable and viewed as a highlighted point on the scope using Z modulation. I patterns are best for setting a sampling instant. Triggering on the data frame sync, we can switch back to a time domain view of the detector input, as well as its output for a visual comparison of the recovered data stream. Increasing the noise in the channel increases the bit error rate of the signal, which we will now measure. Insert a local reference sequence module and error counter module to enable a comparison of the recovered data and local reference sequence data. Patch them to the pulse counter, which will display many errors being detected prior to synchronization of the sequences as expected. A sliding window correlator method is implemented. The errors stop as the sequences are aligned. The pulse count is cleared. Sequences are misaligned again and then resynchronized using the alignment signal like so. After alignment, increasing noise in the channel creates errors, which we can measure to define bit error rates, and use a true RMS module to measure signal-noise ratios of the channel. We can then plot bit error rate versus signal-to-noise ratio for this signaling scheme and compare with theory. We have modelled encoding, skipped the modulation, a channel, skipped the demodulation, and then decoding.